Зовут Крис Бавик или Бавец, если польский вариант. So, Chris.
Chris Bawiec, is how you would say it if you were in the US. So yeah, today I will be talking about just some of the work that I've done for, first what I most recently did in France, working on CMUT transducers, the capacitive micromachined ultrasound transducers. And then after that I will try and talk about some of my previous work that I did for my PhD, which is also ultrasound related, more so to drug delivery and a completely different technology. But first we will talk about the capacitive micromachined ultrasound transducers, which are essentially, it's an ultrasound transducer. It can do the same thing that a piezoelectric ultrasound transducer can do, but they're constructed very differently. You do not use a piezoelectric ceramic, you use silicon manufacturing techniques. And so a piezoelectric ultrasound transducer, as I'm sure you are aware, is constructed of piezoelectric elements. They're ceramics generally, and they conform or they move when you apply voltage to them. And they can be many different shapes and sizes, they are cut and put electrodes on the top and bottom, things like this. Well, the technology for the CMUT is much, much different. It starts off with a silicon disc, and you use the same techniques that you do to make microprocessors and high-end electronic components like that goes in your phone to create an ultrasound transducer. So this is a silicon fabrication, or a silicon wafer. And this is the wafer that is the ultrasound transducer is designed on. This process is extremely complicated, but essentially what you're doing is you start off with a flat wafer and you're adding and subtracting layers such that you could create exactly the design that you want, which in the end is, so you take one wafer and you add and subtract layers in order. So you create a cavity, say, and then you fill that cavity and you add a membrane on top, and then you etch away or remove the cavity. So essentially what this is saying is that we add layers and then subtract them such that we end up with an open space here on top of the silicon wafer, but there's also a membrane on top. And the way that the CMUT works or operates is that it actually takes that membrane or this vacuum cavity and it allows the movement of the membrane, which allows for vibration, which then allows for the ultrasound wave to propagate or be formed. So this is kind of a schematic representation of the CMUT design, where you start off with the silicon wafer, which showed you is approximately yay big. You add a layer of dielectric to it, and then you oxidize some silicon on top. You etch away a cavity to create the vacuum, and then essentially you're adding another layer to put a membrane on top. Now you put an electrode on the top of this, and now you have a capacitor, and you have an electrode down here at the bottom, and now you have a capacitor, or basically two electrodes with a vacuum in between. And so when you apply a positive and negative voltage to the top and bottom, they are attracted to each other. And so since they're attracted to each other, you can deform this membrane by applying a higher and higher voltage, and then by alternating the voltage, or having an alternating voltage, you can vibrate the membrane, and you can cause ultrasound to be generated using this technique. So it has some really useful things that I'll discuss in the future, but really what you're looking at here are hundreds, if not thousands, of elements per transducer. I don't know if I passed the slide yet, where I talked about the differences. I think it was the very first slide. But a ceramic can maybe be like 100 microns to like a millimeter, or maybe even a centimeter in size, where the CMUTs are actually much smaller. In general, each cell, like one of these cells, it is about 30 or tens of microns in size. And by making arrays of these cells, you can actually make any size you want just by adding more and more and more of these elements. and you're able to create an element as large or as small as you want. So you really have a lot of flexibility with the design that you're making. So this is an example of an interstitial probe, meaning a probe that is inserted into, in this case, the brain. And you have, these are the elements, and so this is 2 centimeters right here. And if you zoom in, now you see hundreds of elements within this. And we have over 1,000 elements, or 1,000 cells per element. And in this one, we have approximately 10 elements in this 2 centimeter scene. So we have tens of thousands of cells in here. And now, and these cells here are 30 microns by 30 microns each individual one. So this is kind of the operational mode. So what I said is you have a capacitor and you apply positive and or an opposite voltage on either side of it, and you can cause the membrane to deflect into the vacuum, and it can vibrate to form the ultrasound. Well, you have a few things that are limiting for the CMUT design, and that is if you apply too high of a voltage, that vacuum cavity is on the order of 100 nanometers. And so if you apply too high of a voltage, you can actually cause breakdown of the dielectric element inside and permanently damage and render the probe useless. So you have a limiting breakdown voltage up here that you cannot exceed, or else you cause damage. But also, if you think about it, you actually need to drive these things with two different, you have to apply a DC and an AC signal to them. And the reasoning is if you have 0 volts on the bottom membrane, and on the top you're going between plus and minus, well, it's the difference in voltage that is causing this membrane to vibrate up and down. And so if you, say, apply a 10 hertz signal, or more realistically, a 1 megahertz signal to an ultrasound transducer, it's actually going to end up vibrating at 2 megahertz because it's going to be pulled towards it on the upper half of the cycle, but also on the lower half of the cycle. So if this was around 0, the deflection would actually be twice the frequency that you want. So first you have to give it a DC offset, so that when you do apply the alternating current, you get a linear response from the membrane, or somewhat linear response from the membrane. And so you can have different modes of application. So we apply a DC offset and then apply an AC signal on top of it to generate a nice linear waveform that we're looking for. Well, I was mostly doing my research on therapeutic ultrasound, which used much higher intensities. And so we wanted maximum deflection of our membrane. So we had as much voltage as we could possibly do. And what's interesting about these transducers, I suppose, is that they have different modes of operation. So I said conventional mode, which is very easy to understand. You're just vibrating the membrane on the top. It's going up and down. But if you apply a high enough DC voltage, the center of the membrane actually hits the bottom of the cell, and now you're actually generating ultrasound on the 2 sides, which also essentially doubles the resonant frequency of the device. But if you really want to drive it at maximum amplitude, you want to apply a high DC voltage such that it hits the bottom every time, but also snaps all the way back. And so you really have to find all of these parameters when you're designing the transducer to get the most bang for your buck, I guess. So this is a microscopy of a single ultrasound CMUT array. And this is another example of the CMUT interstitial probe. And this is one element here. There's no scale size here, but similar to the other ones. These are, I think, 30 microns by 30 microns in size. And this is just a DC voltage applied so that it collapsed. So we showed you on the other side, if we apply a high enough DC, then the membrane will collapse in the center, and then just by light microscopy, you're able to see the individual cells and determine the collapse voltage, which was a critical voltage that you were looking for. So some of the advantages of the CMUT are that it has a very broad band response, or it can be driven at many different frequencies. Like it doesn't have a bandwidth that's very narrow, or it's much broader than a piezoelectric element. So you can have a transducer that can receive or send from 2 to 10 megahertz. Very broad band transducer. Works this way for receiving and also imaging, although when you have to do therapy you tend to have to match it, so you're still stuck on frequency. But it also has very high electromechanical coupling or potential for this, meaning that you don't have a whole lot of loss for heat when you're doing this, so it's good for certain therapeutic applications where power is at a premium, and it works pretty well under the MRI machines. Which is good because one of our goals was to do MR-guided ultrasound. So we were putting it inside of the brain, but we wanted to see exactly where we were heating. So it's imperative that we can use this in the MRI. It does have, it's also got a benefit because the silicon technology really lends itself to be mass-produced. It's not really great for R&D purposes. So prototyping is very expensive, and it's an arduous process to get it right. But once you get it right, you can really mass produce these things, and they would practically become disposable devices if you really had a very good design that was done for it. So in mass produced quantities, it is much less expensive than a piezoelectric device.
Chris, maybe there can be some questions.
Oh, sure.
There are several parts. So the first part was general and related to CMUT technology, like what it is.
Yeah, I have one question.
Sure.
Well, about silicon material. Why used just silicon? Maybe it has some issues.
I think really the main reason why you want to why you're using it is because it's well suited for electronic fabrication. Generally speaking, the reason why you would use silicon is because you can use it to make diodes and different electronic components for when you're doing microprocessors and things like that, because you can dope the silicon. So you can create a transistor, you can create a diode right there on that silicon disk. It doesn't have to be silicon, actually. It can be glass, you can do quartz. They definitely are experimenting with many different materials. It's just that the equipment used to process the silicon is already there. And so this technology came because they started doing MEMS devices based upon the foundries that were generating chips, and so the technology is there. In fact, when they make CMUTs now, it's all old stuff. They're using the 100 millimeter technology for the wafer size. Well, the newer technologies is 150 or 200 millimeters. But it's too expensive for R&D purposes, and just Intel and AMD and the big people, they have access to these fabrication labs. So.
Chris, maybe it wasn't clear, but when you said about the depth of this vacuum layer, it's only several nanometers, right?
About hundreds, maybe 100 or 50 to 500 nanometers.
So this bending, it's not as strong as it's shown in the picture. It's like slightly bending.
Yeah. So because it's 30 microns versus 100 nanometers. Yeah. So really, it's really not to scale at all. Yeah. So you have more of it's flat in the center, and then just on the edges you are.
And I have one more question. It was always interesting why this technology was so slow in terms of acoustics, because the start was more than 20 years ago in Stanford, and it was always, it's a new technology, it will just blow up in 1 month. And then after 20 years it's still on the way, so what is the main trouble?
This is everybody loves this question, first of all. Or at least anybody working with CMUTs loves this question. So really it took a long time and a lot of R&D to get it to work. When I was working with it, my prototypes, what I became really good at was breaking CMUTs, was causing them to not function anymore. When you're searching for these parameters that you can use to operate it the optimal way, you're definitely going to break your devices. They're not very robust. That's especially when you're trying to do therapeutic type stuff with them and drive them with high voltages, they are very fragile. But if you were trying to do imaging, there's been a lot of, it really took 20 years might sound like a long time, but it's not really that long of time when you consider the age of piezoelectric elements and things like that. And now they do finally have commercial imaging probes that are made of CMUTs on the market. So, it takes a long time, and it really is expensive to do the R&D processing. When I say that it becomes inexpensive on a large scale, that's because your yields become very high. And the reason why, meaning maybe when you make something, you can use 95% of what you're making. When you're doing it by hand and doing R&D space, sometimes you're lucky if you get 10%. So it can be a very big difference between what you're trying and repeatability. When you're in a big fabrication thing, when you have 95% yields, that's because everything's done with a machine. You're not touching it. You are programming it in, and it is running through all the steps for you. But human error causes lots of problems, and dust. You have to have an extremely. One piece of dust can ruin half of a silicon. Anywhere where that dust is will ruin whatever you're trying to make. Because this is a process to make these is a several week process. It could take a day, every layer that you add or subtract, essentially factor that as 1 day that you're spending to do this. And it's 12 to 20 layers that you're adding and subtracting to create these devices. So any time that anywhere along that process if something goes on, it magnifies the problem. So they're fragile, it's difficult, challenging.
How do you make vacuum there?
How do you make a vacuum?
Yeah.
That's actually not a difficult part because almost all of the devices, so when you do there's two different ways you can do it. One of them makes it pretty easy, and that is you're doing a sacrificial layer. So you create the hole in the CMUT, so you add stuff and then you subtract to create where you want the vacuum to be. And then you add something in there that can be etched away later. You call it a sacrificial layer. And then you put something on top of it. And then when you want to etch it away, you put it into a vacuum and insert a gas that etches it away. So the machine that etches is in a vacuum. So it just creates a vacuum. So as long as you are able to seal the hole in the same step, it's not an issue to create the vacuum. And most of the processes for the adding and subtracting occur under vacuum. It just keeps things cleaner and easier to process. Yes?
Multi-element piezo sources are often made with random coordinates of elements to prevent secondary foci, because they can be dangerous with big intensities. And I see that CMUTs are the right rectangular structure, and are there some problems with that?
Certainly you could. I think there's many different driving strategies with CMUTs. So I would say generally speaking, you have grid-like structures for your elements and your arrays. But sometimes they'll just do a single line. But I don't know if I have a picture here, but there's really some strategies where in one grid, maybe you're not normally applying a signal to one cell, you're applying it to the element in whole. But there are driving strategies where you can actually, just apply the signal to a single cell, and they just have different strategies of, really it's all about measuring afterwards and trying to optimize the design so that you don't have these foci. You don't have to fire everything at the same time. You can really choose where you want it to fire from at any given time. And it's not always great. I'll show you a prostate design where it's really set up as an annular array, and it's more of a radial type design that it's a lot of flexibility. It's really your imagination as far as what you want your design to look like. You have nanometer precision as far as where you want the cell to be, how big you want the cell to be. the shape of the cell. There's circle cells, hexagonal cells, square cells. Really, it's up to you as far as.
Okay, yeah.
So this is a piezoelectric device for treating the prostate. And it's a HIFU device that goes transrectally. It images the prostate, and then it fires a HIFU beam at the prostate itself. Now, I'm going to try and fast forward the second one here. And what we were trying to do, did not work. No. So, we should probably just, I want to fast forward it, but I'm going to wait a second. But basically what it does is, it goes in here, so the center part's an imaging array, and on the outside it's an annular array that is a therapeutic array. And it is generating high intensity ultrasound for HIFU, right? So we are going to heat the tissue in this prostate. But it's going to do one single lesion or thermal lesion at a time. And this lesion is roughly the size of a grain of rice. And it goes in and it fires, and then it moves and it fires and it moves and it fires to ablate the entire volume of the prostate gland. But it also has some different, not the best time, so sorry. I was trying to fast forward for this, but what happens is you also have some elements, and in this case there are about 16 elements, and you can change the depth that you are creating this lesion. Hopefully it'll come up here soon. So it might be it's geometrically focused, but it also can be phased such that you can focus between 3 and 7 centimeters. And it's a time-consuming process, I don't know. But one of the things that we wanted to do was take this piezoelectric design and create a CMUT version of it to improve upon some of the things that were limitations for this design. And one of the limitations is that you really want to put this imaging array in the center here, but it takes up a lot of real estate. And because of the way that it's designed, it needed to be a curvilinear array, and we could fit 192 elements on there. But if we could create a flat surface and have a linear array, we could really improve the imaging. So you can see all the firings sum up to create an ablation everywhere. So what I tried to do for part of my project was to compare what would happen if we could do a CMUT version of this piezoelectric array. In the CMUT version, so this is the piezoelectric array, we have 16 elements here, and they designed a 64 element, so that instead of 16, there are 64 elements from here to here, and it's flat. And we are no longer geometrically focused, but we can still do the phasing focus from 3 to 7 centimeters, but it reduces the volumetric footprint. I mean, it's no longer thick. I mean, we still have about the same width, but also we are able to have a 256 element imaging array here. So we are able to improve upon the imaging of the device. So we had a couple of these fabricated, and so this is kind of the design. And this was actually one of the first slides I showed you, was a picture of the silicon chip, where you basically manufacture a whole bunch of these. You have to cut them in squares, is the way it works. And so they're quadrants, and then you assemble them together, and each one of these is 64 elements, and then they're connected in parallel across here and across here, so that 64 individually addressed elements, and then as you can see, like, those are individual cells for each element. So you have a minimum of, like, so in these ones, maybe 3 or 4 cells in the outer rings, and the inner side you have about closer to 20 rows. And these are designed to the equal area from here. And so we were just trying to see if we could create something that would work as well, if not better, than the piezoelectric version. This is actually microscopy, like showing the collapsed cells for the actual prototype. Let's see if this video takes a long time. But so this is kind of what I was talking about earlier. Maybe we should have gone the previous slide. But as we increase the DC voltage, we hit a point where the cells collapse. And this is actually hopefully a video. And it should collapse around 130 volts. And then as you decrease, you are also having a snapback voltage. Should have probably put this with the other slide. But really, this is just showing more of trying to determine the critical voltages of driving these things. You need to make sure that you operate in a region where you go above collapse and below the snapback region if you really want the membrane to vibrate as much as possible. Maybe I'm gonna keep going.
It can resist for 1,000 times of collapsing and snapbacking?
Yes, but if you one time go too high, then it's so, I mean, it's really critical. And in fact, like there are, I mean, I say that there's just the critical like breakdown voltage, but really there are other voltages as well that are maybe before the breakdown voltage where maybe you're causing some wear to the membrane or something, but it's not so simple as just one value. For the imaging, they last a long time. They're fairly robust, and I was able to run for 24 hours at a low signal, and it worked. Didn't see any degradation in the behavior. So some more pictures of the design of the prototype. This is the actual prototype with, both pictures of the actual prototype. This is with a protective layer on the top. Oh yeah, I covered it.
And you don't need any matching layer, right?
Oh, yeah. So imaging, no matching. Yeah, lots of matching for the therapeutic parts. So they're they're capacitors, so they're very capacitive devices. So you need to if you want to drive them with, if you do not electrically match them, I don't know, you can get 90% reflection or more of your signal. So you really need to do stuff such that you can deliver a large amount of power to them, which is also a challenge. I had to design a matching board for all 64 elements that fits inside of here.
So when you say 100 volts for this typical voltage is 100 volts, but after matching it should be much higher, right? Or it's after matching?
Yeah, so it depends. So generally speaking, when we define it, when we determine these voltages, we are not matching. We're just measuring it at the output. We just deal with the reflection. So that's how we determine it. But yeah, we can. And this is probably part of the reasons why we end up breaking some of them. So, because even if you don't match them just right, then you don't get to quite the voltage you're expecting, and then it's gone. So that was one of the applications, was this prostate probe. The other application was an interstitial brain probe. Now we were working with a hospital in Paris where the neurosurgeon has to treat tumors within the brain. And these are incredibly invasive tumors that are going to kill people. The goal is really to prolong life as much as, and make it better for as long as possible, but these are, already seriously injured people, so much so that they're willing to drill a hole in their head and have a probe be stuck inside. And they use different types of laser interstitial thermal therapy, where you're creating a thermal lesion using a laser tip or an RF ablation. So they drill a hole in this, or freezing. And now with all of these technologies, you don't get very much directionality or conformal lesions. What happens is you're creating a sphere around what you're treating, more or less. Well, the idea is that we could make a probe that was multi-directional with the CMUTs and wrap it around so that we could turn on and off whatever side we wanted. So if we just aim in the center of the tumor, wherever the tumor is, we turn on those elements that we want, and we can treat in that region. This is an unfocused therapy, but it's at about 6 or 8 megahertz, so that you're heating directly in front of the elements themselves. So you can see like 10 different faces. So this kind of, these were the interstitial probes that I showed. These are what I did most of my testing on because they were easier to manufacture, I'm sure. But it's the exact same design between this one and this one. They're just, it's how they're packaged and how they're housed. They're the exact same size elements, but on a probe like this. So we're able to actually use these and generate some pretty good thermal lesions, and these were the ones that were done under MR guidance. So this was for MR guided high intensity ultrasound. So in this case, this is, I don't know how familiar you are with MR guidance, but with MR it's really nice. You can measure
Chris,
temperatures.
what is MR?
Oh, sorry.
Yeah.
Magnetic resonance imaging. So it's this large magnet here allows you to image under using the magnetic resonance.
And there was the question, what is haiku?
Yeah.
Oh, haiku. So you know what HIFU is, I'm
Yeah,
sure.
I know.
So high intensity focused ultrasound.
Yeah.
So this is unfocused. So it's contact ultrasound.
Ah.
So it's just it's in contact. So there's no focusing involved. But you want high intensity ultrasound for thermal ablations.
Yeah.
It's people love acronyms. So this is the. But with the MR guy, like the MR is really like great technology in the sense that you can look inside and determine temperature changes within a tissue from the exterior. So it's really great for things like high intensity focused ultrasound or something where you want to measure the temperature change inside of a tissue. Unfortunately, MRI machines are extremely expensive and the thermometry is not the greatest, but you can still get some pretty nice results. We basically used this probe to see if we could create thermal lesions in brain tissue using pigs, and we were able to do this. This is actually a reconstruction of the MRI image directly, not. And then I will show you the actual, so this is the MRT or MR thermometry image side. So the idea is that you can see a temperature change. You don't really know, basically you have a baseline temperature and you're able to tell how much it's increased or decreased as long as you have this baseline. And so for this side here, what it's showing is that we have a probe in here. After 30 seconds we have some heating. We have more heating as we increase in time. Actually, for 10 minutes, not a whole lot of difference between 2 minutes and 10 minutes here. And then we turn it off and it was cooling. This is just an example of showing. You can actually, like this is like one slice, but you actually can create volumetric images of the thermal heating. So I'm going to stop here for a second. Do you have any questions on the two applications that I described?
Yeah, I have one question
Sure.
about size of this hole which you just make for this.
The brain.
Yeah, in brain.
It's near a centimeter.
Mhm.
But
It's,
this is a typical hole that is usually done for histology, right?
I think so. I didn't make the hole, so, but I was there, and it's
So is
about
it
from
similar to usual laparoscopy when you place endoscope and you see around, or it's just a hole and you place the transducer and only the transducer, not anything else?
just the transducer.
Okay.
Um,
So then it can be smaller than a centimeter, maybe a couple of millimeters.
I think the hole could definitely be smaller. In this case, the hole was not smaller, but it definitely could be smaller. There was no reason. I mean, these animals were sacrificed at the end of the procedure. So, yeah, I think, and I mean, there should be potential to include imaging on these arrays as well. There's no reason why that you couldn't also, I mean, that's kind of a potential or possible advantage, is that you could easily use the same elements for treating, therapeutic treating and for imaging if you have the right electronic stuff. So now I'm going to kind of move on and talk about some just general characterization of ultrasound transducers, which I've done some of. Because basically you have to just measure. It's all about trying to figure out what the transducer does, how well it works, you know, everything. So this is, and you also generally want to compare it to your simulation. So you want to simulate what's going to happen, you want to measure what's happening, compare, hopefully they agree. If they agree, you're happy. Otherwise you go back to simulate, or you figure out what's wrong with your experimental results. So this is back to this prostate probe, some simulation of this annular curvilinear array with 192 elements versus a 256 element linear array. Just as kind of like what's the simulation, but you can see that you are able to get much better lateral resolution with this type of probe than you are with a curvilinear array. You know, kind of showing that it would be better to have this type of array. Now, this is some experimental results with a CMUT array showing the imaging. This is kind of like a typical ultrasound phantom. You have a bunch of pins at different depths, at different sides, and at different you know, angles, so that you can kind of see how well your lateral resolution is or your axial resolution is. This is one of the methods of, so you're firing each, so this is done with it's a commercial ultrasound, or it's a research ultrasound device. So basically you are able to control firing every element individually and do image reconstruction. They have algorithms for you for the most part. This image right here is just checking to see if the transducer works, really. You're putting the probe in here and a plate on one side, and you're firing one at a time and seeing what the intensity of the signal is that gets reflected back. You're sending and receiving for imaging purposes. You see this little line here? That's an element that doesn't work. So you're just going through here. So I did much more therapeutic simulation, but when you're doing the therapy, also you want to kind of, I don't know, for the simulation, you're just generating a pressure field, or using a software that can, maybe a finite element analysis software, or a software that can simulate acoustic fields. And there are a few of them out there, and you can kind of see where the focus of the pressure field is, and if you can simulate the pressure field, then you can also simulate the thermal deposition in the focus of the pressure field, and you can simulate what the lesion shape would be, the size of it would be, how long you would have to have it on for, or what power you would need to have a lesion there in some specified amount of time. So this is a comparison between a 64 element planar CMUT array and the 16 ring geometrically focused piezoelectric array. There's certainly a difference, but you can see that they're similar. So this in red is, these are the different depths. So when you are focusing closer to the transducer itself, you have a much better axial, I guess maybe resolution is a good word, and it's smaller size. When you get further away, the lesions grow in length. But you can see that there's not too much variation between the size of the lesions between the two geometries. So this is a somewhat typical, I don't know, typical testing setup or room, I guess. So what this is a water tank right here, and this is the ultrasound probe sitting on the surface of the water, because this isn't a preliminary probe, so it can't really be submerged very easily, so we don't want to get the top part wet. And what we're doing is we have a hydrophone. I'll just jump to that really fast. We have a hydrophone in the water, and inside here, and basically this hydrophone measures the acoustic pressure at different points where you move it around. But you have all this different equipment here to drive the transducer itself. This is an AC generator that's got 64 individual channels, so you have to plug in all 64 channels individually. You have to drive every channel individually. You also have to have a DC component, so you have to do all of this. You have to have matching, so you want to match all.
16 matching boxes, right?
There are 4 matching boxes with 16 channels per box.
Did you do it?
I did.
Hold it, right? It's like
Well, I put tape to hold it from falling in the water. And then you have a positioning system, so at least that was automated. So you, once it's all set up and running, you send off signals, and you're receiving the signals, and so you're sending it off to every single point, and you're recreating a 2D field. But if you want, and so, and each one takes a finite amount of time, and you have to move in X and Y position. And I don't know how to do holography yet, so I had to do it not just in X and Y, but also in Z direction. So I had incredibly long overnight scans that were near 15 to 20 hours where it was scanning. And this is a 10 by 10 by 20 millimeter region in water. And it takes that long. If you want a high resolution or a higher resolution scan, it takes a very long time.
how much points did you have at each direction?
What was it?
How much points did you have at each direction?
I guess it kind of depends. I think these were like 0.5 millimeter, and these were 1 millimeter in the depth. Probably. I could look it up, but I don't know right now. So what you're doing is, so I needed to compare once again the simulation to the other experimental to simulation. I wanted, like, when they built it, they didn't even know if it was actually going to focus. So it was pretty good news to look to, measure the field, see a focus, see that it really matched up fairly well to the simulation. We were pretty happy with this. 0.5. For our scan volumes, this is a comparison of the two, so actually it didn't look too bad. You have to do, when you're doing these types of measurements, one, you're getting an electrical signal, but then you also have to do some...
According to these images, it's like, if you go back, it's like 10 by 10 millimeters.
This resolution.
It's a step.
Maybe
So
it wasn't the scan region, it was the step size, right?
The step size, yeah.
Okay.
Step size. And then, but also, like, I'm gonna go back one more. So you're sending off a signal, and you have a receiving hydrophone, and you want to catch the signal, not in the first part, where like some of the signals aren't combined quite yet, and not in the last part, but right there in the middle. And if you're right there in the center and you're measuring it and you're just moving back, this is a very simple calculation to do. But if you are moving all around in the field, then you have to adjust where you're looking for, and you have to automate this because you can't sit there forever taking measurements like this. So it actually becomes quite, the software can do it for the most part for you, but you can't have too long of a pulse because you don't want it to reflect off of other things. There's a lot of nuances that you have to look at when you're making these measurements. The holography, I think, would be much better.
But only one layer, not three.
Yeah, for sure. So we have that. So then another big thing that you have to do besides measuring the pressure field itself, but you want to see how much power you have in an ultrasound transducer. And to do that, basically, you are seeing how much force can be acoustic force can be generated. To do this, you can use a force balance, which is essentially a balance or a scale that can absorb the acoustic energy generated by the ultrasound transducer, and you measure it in milligrams, but you can back calculate it into watts. And so what you want to do is see how, because you need a certain amount of energy to create heat, especially if you're creating thermal lesions, so you need to make sure that your device is capable of this, but also to characterize it, like how high do I need to turn it up to get whatever I want. So this was one of the radiation force balance measurements that I did with the CMUT probe, and I told you that we had to combine an AC and a DC voltage. Well, this AC and DC voltage changed the behavior, so it's just another set of parameters that you have to isolate. But as we increase the DC voltage from 80 to 120 volts, that's what these different lines are accounting for, and then increase so the DC is the different colors. The AC is the x-axis here. So as we increase the AC, we get a higher intensity for our device. But you don't just want to measure that, but you also want to measure, like, we're putting a certain amount of electrical power in there, and we want to know how much of that electrical power is getting generated into acoustic power versus how much of it is getting generated into thermal heating. Like, how much loss is there? Like, what's the efficiency of your device? In theory, CMUTs can be perfect, efficient. They're the most efficient device ever. But in practice, they have a lot of room for improvement. So the math shows that you can get above 90% for your efficiency, but my experiments show that you get far, far less. So you want to, you have to explore your parameter space when you're making measurements. You have to vary all of these different things. And so in this case, and this is pretty typical with the CMUTs, when I have a higher DC, which was this yellow line here, we had a bit much higher efficiency. But when we had a lower DC, this blue line here, we had a lower efficiency. And then but somewhere in between 80 volts, this blue line, and 120, this yellow line, we were actually able to get higher intensities. So really, you have to play with it to really get what you want. So for the CMUTs, increasing the DC bias voltage increases the efficiency, but as you can tell, it stops here. Why does it stop here? Because this is 120 volts plus 100 volts peak to peak. So that means my breakdown voltage is right around 200 volts. Well, I can't go any higher. So if I go any higher, then I break it. But if I have a lower DC, then I'm able to increase the AC much more before I hit that breakdown voltage. So one of the things that is currently, people are working on is how can we make the breakdown voltage higher? Because if we could generate more power, if we could just not cause breakdown. So better dielectrics or different schemes to do that. So this one's so this is more of a visual test, but also a very good one. So basically, we want to just see if we apply, if we're generating acoustic pressure, then we should be able to see what's happening. So sure enough, if you put this ultrasound transducer on the bottom here, this is just like a thin membrane, fill it with water, we can actually see the focus, and by adjusting the height of the water, you can actually see whether or not you're focused there. It will go from a point in the center to a ring on the outside maybe, or since this is 4 quadrants, you'd actually get 4 little ripple lines here, so you can see how well your phasing scheme is to focus and see whether or not it's working. So just a visual verification. If you have a really powerful transducer, you can create a fountain or a mist at the surface of the water. I think some humidifiers use this technology. This is another interesting method. This is a kind of using an ultrasound imaging transducer to look at the ultrasound therapeutic transducer's field. So by looking, not so sure on the physics of this one, but you are listening to the sound field generated by the, so this is down here, this is our CMUT probe, and up here we have our imaging probe listening to the sound that is kind of being generated by the CMUT probe from below. And it's just listening, and you are able to reconstruct and see the focus of the beams themselves. They're working on ways to make this, right now it is a qualitative, you can't really tell the pressure level or anything, but they're attempting to use this technology to quantitatively determine the pressure levels of the ultrasound field. And I think it's very similar to the technology or the theory behind holography, but you're measuring on many elements at the same time as opposed to.
Maybe Chris, here you can add that just to show the example of collaboration between different countries, that this work was done by a postdoc from Japan, right?
Yeah, so this is so I was in France, but this is a postdoc from Japan. Actually, he was a PhD student at first when he was working on this, and then he came back as a postdoc in Japan. Well, he came back 3 times in 2 years because it was such an interesting technology, and they were really trying to get it worked out. But it was lots of different collaborations going on. It was nice.
Well, Chris, sorry.
Yeah. Another thing, obviously, we want to see if it can heat tissue. So a good way to do that is to use an IR thermometry or an IR camera. What this is showing is the same setup as before once again, but we floated a thin absorbing pad on the surface of the water, and we had an IR camera up at the...
What is IR?
Infrared camera to measure the temperature change in the surface of the device. I don't have any pictures, but maybe even a better method is to purchase some chicken breast or something and just create a thermal lesion to make sure that you are, see if you can cook it, then you can create a thermal lesion. So this is also a very useful test for your device. This is actually one of my more favorite characterization tools. This is a laser vibrometer. So it's similar to an interferometer, but what it does is it measures vibration at a very specific point. So it uses a laser, and it can, depending on the laser spot size, it can measure the vibration as long as what you're looking at is reflective. You can measure vibration, and you can measure displacement, and you can measure it in real time. So you can look at the face of a transducer or a CMUT cell or something, and you can really measure how much the displacement is with the voltage applied to it in many different situations. You can do it underwater, a little bit of water if you want, not just in air. And you get something very similar to like what a hydrophone, you can extract signals from the vibrometer such that you just get a displacement in time signal, and you can reconstruct the face of the ultrasound transducer. With a piezoelectric ceramic you can do it, but you can also do it with the CMUT cells. And with this particular device, it goes down to 3 nanometers spot size for the laser, so it's very well suited for a CMUT, which needs very small spot sizes, or sorry, not 3 nanometer, 3 micron. 3 micron, big difference. But because we also had vibrometers that have a 30 micron, which sounds small, but that's great for a piezoelectric element, but it's not great for a CMUT. You only see the gross vibrations. But so this, once again, plenty of electronics to set everything up. This is the whole system here. These things cost upwards over $100,000 for a laser vibrometer. So I had to travel to the middle of, not where I was working in France, but another location in France, just so I stayed there for a week so I could make some measurements.
And where did you go?
Tour. So right outside of Vermont, the Grumman lab, there's a university in the center of France. Very pretty town. And so this is an example. This is the actual scan that was reconstructed. This is one element. This is just this little part right here, and actually just a tiny bit of it right here. We ran the scan overnight to make this image right here. So we ran it overnight, and what we were seeing here, and I've since learned some new things, but basically we were driving just one element in, and this is all the same electrical connection here. So we apply one signal, and all of them, you would expect them to all be in phase. Let's see if I can get it to run again. You would expect them to all be in phase, but you can actually see how it's a little more on the outside than on the inside, and you get some variations in the, it's nothing simple. It's basically the best way to look at this. And this element's not being activated, but yet it is also vibrating. So, well, maybe not. But there are, really you have like different things. Now, I've since learned, quite possibly, is that we are creating a disturbance in the water, so which refracts the laser, which causes it to maybe look like it's vibrating. But it's really nice to be able to have this kind of resolution. And you can, this is actually not even this 3 micron size. Like, we can actually create an image of one single cell that is, has quite a high resolution to see the complex vibrations of the structure. And also with a piezoelectric transducer, you can really look at the surface waves that are generated and other complex things using a device like this.
So maybe I have a
Sure.
general question about PZT versus CMUT.
Sure.
Which design or technique actually provides the highest possible intensity? Without breaking the transducer or...
Without a doubt, well, PZT, but I think you can generate even higher with other lithotripter type devices.
How much higher, the magnitude of the difference?
I honestly, I don't know. I haven't really explored the limits of piezoelectric elements, but I would say I think it's not uncommon for
Chris, I think
hundreds.
that you showed it. It was like about 5 watts per square centimeter.
Yeah. So I know what it is for
5 watts?
CMUT. I can get about 10 watts per square centimeter with the CMUT.
About 5 times, I guess. Yes.
So I don't know exactly what it is for piezoelectric. But
It's
for
about 50, I guess.
Okay.
So 10 times. Yes.
Yeah, order of magnitude difference.
So it can be applicable, say,
yeah.
for histotrips, yes, it's to...
It's actually not that simple.
Yes.
50 it's for short time,
yes.
and
This is
this CMUT
continuous,
probe
right?
was continuous. For continuous, usually when people work, they try not to go above 5 or 10.
And
So,
then
yeah.
if I use it for pulses, if I use CMUT for pulses, maybe I may
For
apply...
pulses, probably it's not possible to go higher with CMUTs,
Yeah.
but with composites of piezo, you can go higher.
Mhm.
So that's
Yeah.
for pulsing, maybe it's obvious that PZT is better.
The CMUT contains of small cells at school, so it's even smaller. It's even smaller than
Yeah.
piezo composites.
So the interstitial probes that we were using for the brain application, we were able to generate 10 watts per square centimeter with. But I think it was Gen 3, Gen 3 or 4 for the prototype of that, maybe even more.
But it's much more expensive, yes? CMUT is more expensive.
For prototyping.
Mhm.
And also you have to make many of them because you're going to break a lot of them.
Yeah, because you have a rule, yes, how to do it. Mhm.
But for the interstitial application or for future applications, really the goal would be to almost create a disposable probe. You could really use it anywhere, and it should be inexpensive enough such that you wouldn't have to worry about sterilizing it or something like this, or you could use. So for this probe though, this was second generation, almost first generation, not a whole lot of difference. Maybe we got a bunch of first generations, but with different passivation thicknesses or layers. So you have the raw CMUT but you can't just have the metal being exposed. Well, it depends if the ground's on the top or not, but you have to add a silicon layer or a parylene layer, so there's different things that you can put to protect it, but this affects the way that it works. So we got a lot of different probes with different types of passivation or protective layering on the front. But this, we could hit 5 watts per centimeter squared, but they did not last for very long. So I would get some elements that I could use over and over and over again, hit 5 watts per centimeter squared every time when I was measuring them. And then I'd get other ones, like even on the same chip, that wouldn't work. So, in fact, like a lot of these earlier, like this, I only have 28 of 64 elements working. So, it's can be frustrating.
But they were.
So. Now, that was all stuff that I had done in the past couple of years when I was in France, working with CMUT cells. For my PhD, I was working on something completely different. So it was ultrasound, and therapeutic ultrasound, but it was quite different. So with imaging and the therapeutic ultrasound that I was recently speaking of, 1 megahertz, 3 megahertz, 6 megahertz, in the megahertz range. Most conventional imaging is maybe 1 to 10 megahertz. Unless you're getting really fine structures, you can go up in frequency, but you generally don't go down. But for therapy, you want, there are some benefits that can be had with a lower frequency device. One of them is lower frequency means that you can penetrate deeper within the tissue, but also you can induce certain physiological changes possibly easier. So in terms of cavitation, the threshold for cavitation is actually much lower at a lower frequency than it is at a higher frequency. Yes. And so, I don't know, maybe you're familiar with it, but they use ultrasound sometimes for physiotherapy, for if your muscles are sore or you go work out. And so it's been a technology that's been used for a long time. It's really hard to get solid data on why it works or how it works, but they use it, and they use it a lot, and it's an industry that is very common. And one of the more common ones out there, and I think a very common way that they use it, is they use devices that are around 1 megahertz. But they use this 1 megahertz device, and they actually pulse it, or have like an amplitude modulation, or a duty cycle, perhaps, which gives it an overall frequency more in the 20 to 100 kilohertz range. So you have your 1 megahertz wave, but you're amplitude modulating it, and if you look at it on a like a more bigger scale, you're actually at a much lower frequency. So there was a hypothesis that by using this lower frequency, we could generate some of the same effects that the physiotherapy device does, but just using the lower frequency and not the higher frequency. And also they happen to have this nice new technology of flexural transducers have been around for a long time for military applications and underwater acoustics, but they were able to miniaturize this flexural transducer. And what a flexural transducer is a piezoelectric element, ceramic disc, that is capped on both sides. Well, in this case, a flexural transducer element is this, and it's capped on both sides with metal end caps. And these are kind of symbol-like end caps. And what happens is when you apply a voltage to a piezoelectric element, it shrinks on the ends. It shrinks and grows on one dimension, and shrinks in the other dimension, grows in the other. Well, these metal end caps amplify the displacement. So when it shrinks, this gets bowed out, and so now instead of displacing a few nanometers, and now it's tens of nanometers, or it really amplifies, I think up to like 40-fold the displacement that you're seeing. But not only does it do that, but it changes the resonant, you can induce other resonant modes within the transducer such that it operates fairly efficiently at a much lower frequency. So with like a 2 millimeter or 1 millimeter ceramic disc, you can now induce a mode where you're able to drive it at 20 kilohertz or 40 kilohertz fairly efficiently. And so now we can create something that is quite thin that generates low frequency, which is somewhat novel because generally speaking with piezoelectric elements, not CMUTs, you can, it's based upon the thickness of that generates the resonant frequency of the device. So like a half wavelength of the half wavelength thickness determines the resonant frequency of the ceramic, and since I don't know, you can help me out here, but I think 1 megahertz. Is it 1 megahertz is 1.5 millimeters?
It's about 2 millimeters.
2 millimeters. 1 megahertz is 2 millimeters. Is the so 1 millimeter thickness of PZT is 2 megahertz. Right, is 2 megahertz resonant frequency. So if you want to bring that down to, you want not 2 megahertz but 2 kilohertz, at several orders of magnitude less. So you're actually looking at centimeter thick piezoelectric elements if you want to generate something on the order of 20 kilohertz.
Even more.
I think it's around 7.5 centimeters for 20 or 40 kilohertz. And but so it's not feasible. It's not feasible, especially if you want to use it for a medical type application. You're generating the amount of voltage that you would need to drive it also would be high. So now, so we have this technology, we want to test it out. So what we've tried to do is use it to see how can we interact with the tissue, and what is this going to do? What can we do with this device? And one of the ideas was, I mean, they use it for physical therapy, but maybe we can also use it to stimulate the cells to induce a healing type effect. Now, we were working with some doctors that were dealing with diabetic and venous ulcers. So these are patients that get wounds on their legs and their feet that last for weeks and weeks and weeks, and they never heal. And we wanted to see if we could maybe induce some healing type effects. There was some preliminary data that showed that we were getting we were able to cause cells to proliferate more in a petri dish by applying some ultrasound to them and other things like that. So we thought maybe we could try it with this application. So we fabricated these devices, but really we want to know, like, how is this working? Like, we want to look at all the different things that are working. I guess we'll start with the results, which is so what it turns out is that we were able to accelerate the healing of these wounds. It was kind of an interesting study because we were able to kind of build these devices, test them in vitro, but there's no animal model for it. And because it's not only is it low frequency, but it's also low intensity that we're looking at. It's like a very safe low intensity, around 50 milliwatts per centimeter squared, 100 milliwatts per centimeter squared. So there was, there was no real issue, and we kind of wanted to keep it this way because if we keep it this low, then the FDA is happy with us, and we can actually get this product through the market very rapidly without nearly the number of clinical trials that would be necessary if we up the power at all. So really, I mean, we just wanted to keep under this threshold so that we could possibly do that. And we did have, I mean, the number of patients on this was very low, so it's not quite a smooth sailing quite yet, but with our preliminary studies we really saw some great results. Now, why does the ultrasound, or how does the ultrasound affect the tissue? I mean, there are many different ways. I mean, what we were trying to do is measure the different forces that could be generated by our 100 milliwatts per centimeter squared ultrasound. There's many mathematical models, but also of measuring these forces, but also what are the physical mechanisms that are occurring. So we looked at a lot of different things, and it turns out that your body's cells react to mechanical stimulation, and an ultrasound wave is a mechanical stimulation, and it can generate different types of forces, a radiation pushing force, a shear forces, and it turns out other people have looked at these things too, and things like opening the ion channels within a certain cell to activate certain things happens more often when you apply an ultrasound, even at these low frequencies, in this case 500 kilohertz, but as low as 20 kilopascals, like very low pressures. And also, proteins you can actually cause conformational changes in proteins using mechanical forces. Now, this is just a list of the many different proteins that are affected by mechanical forces that could be caused by ultrasound. And then one that I'm sure you've also talked about a little bit is cavitation, but this is like a great slide from a drug delivery paper that I've used several times. But basically, you know, if you do have bubbles, you have a lot of secondary forces that are occurring within the tissue, and these bubbles can really cause all kinds of effects to the body. I mean, the sound itself can maybe cause some damage or some stimulation to the cellular structure, but you can have a bubble. If there's a bubble there, then that bubble is going to vibrate. That bubble is going to create shear forces. That bubble can collapse and create a shock wave and break through the lumen here, or these microjets that occur also when it's close to an interface. Now, it doesn't have to be like an air bubble or a gas bubble. These can be bubbles that you inject into the body as well. So these bubbles can contain drugs on the inside of them, on the outside of them, in the lipid bilayer of them, and you can really like target different different regions if you want. You can put markers on the outside. So there's all these different types of microbubbles that are used, maybe not just for like improving imaging, which they're currently used, but you can use them for targeted drug delivery and stuff like this. But yeah, so I mean, if there are bubbles, which there are bubbles in the body, they can cause these secondary forces that will affect. Oh, nice. So you have radiation force, stable cavitation with microstreaming and shear stresses, inertial shock waves. I remember most of them. So then we have, and then there's even different models too. Like say we don't have bubbles, right? So there's a lot of evidence that maybe these bubbles are, you know, undetectable, or maybe not even there with noticeable with the ultrasound itself. And I think and this is just one of the models out there that's saying, well, maybe the cell itself acts like a bubble. Like maybe the lipid membranes on the outside can behave such that they themselves are being pulled apart and pressed together. I mean, you're applying a mechanical wave that has a compression and rarefaction, or like, you know, you're compressing and pulling apart the cell on every cycle of the sound wave, and this can have its own effects that are associated with it. This is a Krasovitsky-Kimmel model for intramembrane cavitation. It's a group in Israel that I was working with. My PhD was actually in Philadelphia, but we were also collaborating with a group in Israel. And then I don't have, I think, all right, so before I get to that, I just want to say that we also did some drug, so for the wound healing, we weren't trying to push drugs through the skin. We weren't delivering drugs necessarily. But what we did do is we hypothesized that we could push drugs through the skin, or perhaps we could accelerate the delivery of drugs through the skin using ultrasound. So with the same, with a different group in Israel actually, we tried to do some drug delivery where it's the same exact transducer that we were using before, but we were trying to see if we could increase the rate of delivery of betamethasone, which is an anti-inflammatory drug, into the paws of mice. And what we found was that by the application of ultrasound plus the application of the drug, we were able to reduce the inflammation more so than with just the drug alone. So we really believe that the combinatorial effects of a device like this with the drug can increase the efficacy of the drug perhaps, or at least the rate of delivery that is going there. So my So I guess before I'm done, I should ask if you have any questions.
I think we have about 10 more minutes before the next lecture starts here. So if you have any questions to Chris about his scientific work or even any other questions, you're welcome.
Is this Lyon?
This is Lyon. So yeah, I don't have Drexel, but this is France. They have a very nice ultrasound group there. A good mix of undergrad, well, mostly graduate students, I would say, and graduate students, postdocs, researchers.
Where are you?
Can you guess?
Glasses.
It was sunny. So.
Good. Thank you.
That's great. Thank you, Chris, so
Yeah.
much.